Well, today we're doing a deep dive into something that helps make that happen. Chemical maps. Specifically, we're looking at potential energy surfaces, or PES.
Ah, PES. Good clarification up front.
Right, because you might have heard of photoelectron spectroscopy, also PES, which is used more for, like, analyzing surfaces.
True, related name, but a different beast. We're focused on the theoretical energy maps today.
Exactly. So our mission here is to get a real handle on how these conceptual landscapes, these maps, help chemists navigate the world of reactions.
And hopefully without getting totally lost in the heavy math side of things.
That's the plan. We're exploring the ideas from our source text. Ready to jump in?
Let's do it. So, potential energy surfaces. What are they, really?
Okay, yeah, let's break that down.
Fundamentally, it's about how the energy of a chemical system, think molecules reacting, changes as its atoms rearrange themselves.
So, like, as the bonds stretch or bend or break.
Precisely. Imagine playing with magnetic building blocks. Connect them one way, the structure has a certain energy. Connect them differently, the energy changes.
Okay, I can picture that.
A potential energy surface is basically a map showing all the possible ways the atoms could be arranged and the energy that goes with each arrangement.
A map of energy based on geometry.
You got it. And understanding this map helps us predict which arrangements, which molecules are stable and likely to actually exist.
So you described it as a landscape earlier, like with hills and valleys.
Exactly. That's a perfect analogy. Picture a landscape where the height at any point tells you the energy of the system when the atoms are in that exact configuration.
Right.
Now, here's where it gets a bit wild. It's not just a 3D landscape like we're used to.
Uh-oh. How complex are we talking?
Well, for a molecule with n atoms, the PES can have, wait for it, 3 and 6 dimensions.
Whoa. Okay, that's a lot of dimensions. Hard to visualize.
It is. It reflects all the ways the atoms can move relative to each other, minus the whole molecule just floating or spinning. For linear molecules, it's 3 and 5.
So mathematically complex, for sure.
Definitely. But the real power isn't in visualizing all those dimensions at once. It's about understanding the key features, the landmarks on that landscape.
Okay, landmarks. Like, what should we be looking for on this multidimensional map?
The most important ones are the minima. Think of them as the valleys.
The low points.
Exactly. These represent stable molecular structures. So your reactants, your products.
The things that actually stick around for a while.
Right, and maybe any intermediate species that form briefly during the reaction. And the depth of the valley tells you how stable that molecule is. Deeper means more stable.
Like a ball rolling downhill and settling at the bottom. It takes energy to push it out.
That's a great way to think about it. Stable things need energy to change. So valleys are stable molecules.
Okay, got the valleys. What about those mountain passes mentioned in the outline?
Ah, yes, the saddle points. These are critical. They're like the lowest pass over a mountain range connecting two valleys.
Okay.
In chemical terms, these saddle points represent transition states.
Transition states, those are the really short-lived, high-energy moments in a reaction.
Exactly. Fleeting arrangements of atoms that the system must pass through to get from the reactant valley to the product valley. They're like the bottleneck of the reaction.
A bottleneck.
Oh.
Okay, so finding these is important for reaction speed.
Crucial. Identifying them helps us understand and sometimes control how fast a reaction goes.
And that high point, the peak of the pass,
Yeah.
does a really high peak mean the reaction is basically impossible?
Well, that height is key. The energy difference between the starting valley, the reactants, and that saddle point, the transition state. That's the activation energy.
Activation energy.
Right.
Right. Heard that term before.
It's like how high you need to push that ball up the hill before it can roll down the other side.
So a higher activation energy means a bigger hill to climb.
Exactly. Which means a slower reaction because fewer molecules will just happen to have enough energy kicking around to make it over that barrier.
Okay, that makes sense. Understanding that must be huge for, like, industrial chemistry.
Absolutely. Speeding up reactions you want, slowing down ones you don't, it all comes back to these energy barriers.
So the path from one valley over that saddle point and down into the next valley, that's the reaction pathway.
Precisely.
Yeah.
We often talk about the minimum energy path, or MEP. It's the most likely route, the lowest energy trail connecting reactants to products through that transition state.
Like the most worn trail over the mountain pass.
You got it.
And the height of those mountains or barriers themselves, you understand, that determine speed.
Yes, those energy differences act as barriers. A high barrier means high activation energy, slow reaction. A low barrier or even no barrier
Needs a fast reaction.
Yeah.
Maybe even spontaneous.
Exactly. So the PS gives us huge insight into the kinetics, how fast things happen.
Now, the outline also mentioned plateaus and flat regions. That sounds less dramatic than peaks and valleys. What's happening there?
Good question. Even those flatter areas tell us something important. A plateau or a broad, flat region on the PS suggests the molecule might be quite flexible.
Flexible, like it can wiggle around easily?
Yeah, it can change its shape, its conformation, without a big energy cost. Think about long-chain molecules, for instance.
Ah, okay. So that could be important for, say, biological molecules that need to change shape.
Definitely. That flexibility can be crucial for function. Or a flat region might mean there are several different arrangements of atoms that all have very similar energies.
I see. So not just one defined low point, but a sort of shallow basin with multiple possibilities.
Kind of like that, yeah. Still informative.
Okay, so we have this amazing conceptual valleys for stability, passes for transitions, paths for reactions. But how do chemists actually make these maps? They can't just, look at the molecules, right?
Right. This is where computational chemistry becomes absolutely essential. These PES maps are generated using powerful computers and the principles of quantum mechanics.
Quantum mechanics. Okay, Here we go.
Yeah. Essentially, it involves solving the Schrödinger equation. That's the fundamental equation describing how electrons and nuclei behave in atoms and molecules.
Solving the Schrödinger equation sounds computationally intensive.
It absolutely can be, especially for anything bigger than a very simple molecule. But the idea is you solve it for a specific arrangement of atoms, a specific molecular geometry.
And that gives you the energy for that specific arrangement.
Exactly. You get the electronic energy for that fixed geometry. We use various methods, approximations, like Hartree-Fock or DFT, technical names, but they let us calculate that energy.
So you calculate the energy for one arrangement, then another, then another?
Pretty much. But there's a key simplification that makes this practical for most systems. It's called the Born-Oppenheimer approximation.
Born-Oppenheimer. Okay, sounds important. What does it do?
It's crucial. It basically says that since nuclei are so much heavier and slower than electrons, we can kind of treat their movements separately.
Decouple them.
In a sense. We calculate the electron energy, assuming the nuclei are fixed in place. Then we move the nuclei slightly, recalculate, move them again, recalculate.
So you calculate the energy at a whole bunch of different atomic positions, like taking elevation readings across a mountain range.
That's a perfect analogy. You calculate the energy at many, many points, systematically varying the geometry. Then you use mathematical techniques, fitting or interpolation, to essentially connect the dots and build the entire continuous surface.
The computer fills in the gaps to create the complete energy landscape.
Exactly, generating the map from those calculated points.
Okay, so once we've gone through all that computational effort and we have this map, this PES, what information can we pull out of it? What does it tell us about real chemistry?
Oh, a huge amount. Firstly, as we touched on, it reveals the reaction mechanism.
The step-by-step process.
Right. How reactants actually turn into products. It shows you the sequence, including any intermediates in their valleys and the transition states on the passes. It answers that how question.
That alone seems incredibly valuable, seeing the whole sequence laid out. What else?
Secondly, reaction rates and feasibility. We already talked about activation energy, the barrier height telling us about the rate. Lower barrier, faster reaction, kinetically favorable.
Right.
And by comparing the energy of the reactant valley to the product valley.
I can tell if the reaction releases energy or needs energy.
Exactly. Does it go downhill overall, exothermic, thermodynamically favorable, or uphill, endothermic, less favorable? So kinetics and thermodynamic.
Wow. So it predicts the path, the speed, and the overall energy change.
Yep. And there's more. The shape of the PES around the minima, those stable valleys, is directly related to how the molecule vibrates. The curvature of the valley dictates the vibrational frequencies.
No way. So you can connect this theoretical map to actual experimental measurements.
Absolutely. You can compare the predicted vibrational frequencies to data from things like infrared or Raman spectroscopy. It helps interpret those experimental spectra.
That's a powerful link between theory and the lab bench.
It really is. Plus, you get fundamental molecular properties straight from the PS. Things like the exact bond lengths and angles in the stable molecule, that's the geometry at the minimum.
At the valley.
And bond strengths are related to how deep and steep those valleys are. And for really detailed stuff, you can use the PS to simulate reaction dynamics, how energy flows during the reaction, which products might be favored under different conditions. Really advanced insights.
Okay, this PS sounds amazing. But you mentioned earlier, visualizing something with, 3 and 6 dimensions is basically impossible for our brains.
Right. Totally impossible. So we have to use simplified representations.
How do we do that?
The most common way by far is the 1D reaction coordinate diagram, or just energy profile.
Ah, the diagrams you see in textbooks with energy on the y-axis.
That's the one. It's essentially a slice through the high-dimensional PES taken along that minimum energy path we talked about.
So it plots energy versus reaction progress.
Yeah, versus a reaction coordinate that sort of represents how far along the reaction is from reactants over the transition state peak down to products.
So that familiar wiggly line with peaks and valleys, that's our best simplified view of this complex landscape.
It is. It captures the most crucial energetic features along the most likely path. Incredibly informative, even though it's just 1D.
Are there other ways to visualize it?
For simpler systems, maybe where only two geometric things are changing a lot, we can sometimes use 2D plots.
Like a contour map.
Exactly like a topographical map. Lines connect points of equal energy. You can visually see the hills, barriers, and valleys, minima, based on the contour lines.
Okay, I can picture that.
Or sometimes you see 3D surface plots where energy is the height above a plane defined by those two changing geometric variables. Gives a more direct landscape feel, but still only for 2 dimensions changing.
Right, still a simplification, but maybe more intuitive for some systems. Okay, so let's sum up the why. Why are these PES maps such fundamentally useful tools for chemists?
Well, for so many reasons. Fundamentally, they give us a deep, basic understanding of chemical reactivity. Why do things react the way they do? The PES provides answers at the atomic level.
Moving beyond just observing what happens to understanding why and how.
Precisely. And that leads to incredible predictive power. You can often predict the pathways, the products, maybe even the rates for reactions that haven't even been done experimentally yet.
So you can map out unknown chemical territory before you even step into the lab.
That's the goal. It's hugely powerful for exploring new chemistry or complex systems.
And presumably for understanding experiments that have been done.
Absolutely. If you get weird results in the lab, an unexpected product, or a reaction that's way too slow or fast, the PES can often provide the theoretical explanation. It helps interpret experimental observations.
Makes sense.
And maybe most excitingly, it's crucial for design. Designing new reactions, designing better catalysts.
How does it help with design?
By understanding the energy landscape, especially the barriers and transition states, chemists can figure out how to change that landscape. How can we lower this barrier? How can we make this pathway more favorable?
Ah, so you can use the map to figure out how to, like, bulldoze a lower path through the mountains.
Well, in a way, yes. Especially in catalyst design, finding a substance that offers an alternative reaction pathway with a much lower activation energy. That's all about manipulating the PES.
It really sounds like an indispensable tool. But are there catches, limitations we need to keep in mind?
Oh, definitely. It's a model, after all. A major limitation is computational cost.
Right. You mentioned solving Schrödinger's equation is tough.
Extremely tough, especially for big molecules or complex reactions. Calculating an accurate PEs can require massive amounts of computer time, even supercomputers.
So it might not be practical for everything.
Exactly. And the accuracy depends entirely on the computational methods used and the approximations made. Remember Born-Oppenheimer? That's an approximation. Sometimes it breaks down.
So the map might not be perfectly accurate.
It won't be perfect. Also, standard calculations are often done for molecules in isolation, like in the gas phase.
But most chemistry happens in liquids, right? In solvents.
Precisely. And solvents can have a huge effect on the energies, on the PES. Including solvent effects accurately adds another layer of complexity and cost.
Okay, that's a big one. Anything else?
Well, the standard PES describes the energy landscape, but it doesn't always fully capture the dynamics. How molecules actually move on that surface, the role of their kinetic energy, some subtle quantum effects like tunneling. Those aren't always included in a basic PEs calculation.
So it's an amazing map, but it doesn't tell the entire story of the journey.
That's a good way to put it. It's a fantastic essential guide, but there are nuances it might miss.
Good to keep in mind. Now let's circle back quickly to the other PES, photoelectron spectroscopy. You said it was different, but how does it connect to these theoretical energy maps?
Right. So potential energy surfaces are theoretical calculations. Photoelectron spectroscopy is an experimental technique.
Theory versus experiment.
Exactly. And PS experiments provide really valuable data that we can use to check, to validate our theoretical PS maps.
How so?
Well, for example, PS experiments measure ionization energies, how much energy it takes to knock an electron out of a molecule.
Okay.
We can calculate those ionization energies using our theoretical models related to the PES of the original molecule and the ion it forms. Comparing the experimental value to the calculated one is a direct test of the theory's accuracy.
Ah, so the experiment gives you a number, the theory gives you a number. Do they match?
Ideally, yes. Or at least they should be close if the theory is good. Also, photoelectron spectra often show fine structure related to molecular vibrations.
Vibrations again, like you mentioned with IR and Raman.
Similar idea. This vibrational structure tells us how the molecule's geometry changes when it loses an electron. And that change in geometry is directly related to the shapes of the PES for both the neutral molecule and the ion.
So more detailed experimental data to compare against the theoretical map features.
Exactly. And then there's surface science. Techniques like X-ray photoelectron spectroscopy, XPS.
That's the surface analysis one you mentioned earlier.
Right. XPS can map out what elements are present on a material's surface and what chemical state they're in. It creates a different kind of chemical map, a spatial one showing composition across the surface.
So not an energy map, but a what's where map.
Correct. But that's crucial information for understanding things like catalysis, where reactions happen on surfaces. And those surface reactions themselves are, of course, governed by their own underlying potential energy surfaces.
I see. So the experimental PES-XPS tells you about the surface players, and the theoretical PES describes the energy game they're playing.
Nicely put. They are complementary tools, both incredibly powerful for understanding chemistry, whether it's molecules reacting in solution or on a catalyst surface.
This has been, wow, a really fantastic deep dive into potential energy surfaces. These mostly invisible but incredibly powerful chemical maps.
They really are fundamental to how we understand reactions.
It's just amazing to think that chemists can chart the energy course of a reaction, sometimes before it even happens in a beaker.
Yeah.
So, thinking about the whole discussion, what's the biggest takeaway you'd want listeners to have?
I think the core message is that potential energy surfaces are these essential theoretical maps. They give us a really deep understanding of how and why chemical reactions happen. They show us the paths, the barriers, the stable points.
The mechanisms, the rates, the feasibility.
Exactly. And their real power comes from prediction, figuring out what might happen, interpretation, understanding what did happen, and design, figuring out how to make new things happen.
Prediction, interpretation, design. That really covers it. So here's a final thought to leave you with. Knowing that chemists can map out these intricate energy landscapes for reactions, what possibilities does that open up?
Yeah, think about creating entirely new materials with specific properties.
Or solving big chemical challenges, maybe in energy or medicine. Challenges you might even see in your own field or daily life.
It really makes you consider these invisible forces that shape everything around us, doesn't it?
It really does.
Yeah.
Something to ponder.